Hello everyone. Today we're going to solve a problem in chapter 7 of thermodynamics, which is all about the refrigeration cycles. So what you can see is the problem that we are going to solve. A heat pump that operates on the ideal vapor compression cycle with refrigerant 134A is to heat a house and maintain it at 23 degrees Celsius by using underground water at 10 degrees Celsius as the heat source. The house is losing heat at a rate of 60,000 kJ per hour, and the evaporator and condenser pressures are 3.2 and 8 bar respectively. Determine the power input to the heat pump and the electric power saved by using a heat pump instead of resistance heater. Before we start to solve our problem, these are our given values. First, we have the rate of losing heat is equal to 60,000 kilojoule per hour. We have also the temperature of the house maintains is equal to 23 degrees Celsius. And then the temperature of the underground water is equal to 10 degrees Celsius. And then we have the pressure of the evaporator is equal to 3.2 bar. And then lastly, we have the pressure of condenser is equal to 8.0 bar. So refer to steam table. At the pressure of evaporator, we have 3.2 bar. And then the specific enthalpy of vapor is 251.9 kilojoule per kilogram. And then the specific entropy of the vapor is 0.9301 kilojoule per kilogram. And then at the pressure of the condenser, we have 8.0 bar. So the specific enthalpy of the vapor is 267.3 kilojoule per kilogram. And then the specific enthalpy of the liquid is 95.5 kilojoule per kilogram. So this specific enthalpy after throttling is equal to before throttling. So is equal to 95.5 kilojoule per kilogram. The expression for the house heat loss is equals to the mass flow rate of refrigerant times the quantity of specific enthalpy of the vapor minus the specific enthalpy of the liquid. So we will plug in the values because we are looking for the mass flow rate of the refrigerant. So 60,000 kilojoule per hour times the quantity of 1 hour over 3,600 seconds. So we will cancel out the R is equals to the mass flow rate refrigerant. So times the quantity of 267.3 3 kilojoule per kilogram. Minus 95.5 kilojoule per kilogram. So our answer is 0.970 kilogram per seconds. So this is the expression for the heat input to heat pump. So we will substitute the values. So we have 0.0970 kilogram per second times the 267.3 kilojoules minus 251.9 kilojoule per kilogram. Thus, the heat input to heat pump is 1.4938 kilowatts. So this is our answer in question number 1. So this is the expression for electrical power without the use of heat pump. So plug in the value. We have 60,000 kilojoule per hour times the quantity of 1 hour over 3,600 seconds. So cancel out the hour. So our answer will be 16.66 kilowatts. We are solving now the last question in this problem. So this is the expression for electrical power saves without the use of the heat pump. So we just plug in the values, which are 16.66 kilowatts minus 1.4938 kilowatts. Calculating this, we can get the answer. So our final answer in the last question is 15.1662 kilowatts.